Hello, ladies and gentlemen. Thank you for joining us today in Kemet's Design It Day. We are very glad to see you here today with us. My name is David Adib, and I am Kemet's Senior Technical Marketing Engineer based here in Florida. The topic of this session is decoupling and filtering. And our speaker for today is Olivia Williams. Olivia is one of Kemet's field application engineers. This session is scheduled for a total of 30 minutes. During this session, you can send us your questions using the Q&A function in your Zoom window. Please do not use the chat function. We will try to get to as many questions as time permits. With that said, I will turn it over to Olivia to get started. Olivia, please go ahead.
Thank you, David. So like David said, I'm Olivia Williams. I'm one of the FAEs on the West Coast here. I graduated with a bachelor's in electrical engineering from the University of Mississippi and have been working at Kemet as an FAE for about 2 years now. But let's move on to some more interesting things. So let's talk about the fundamentals. So first off, for decoupling and filtering, we need to kind of differentiate our topics. So sometimes they're thought of as the same thing, but can actually have, that can actually be a bit different. So decoupling is when something is given up, whereas filtering is passing something along. So to illustrate this, let's look at a microprocessor block diagram here. So we've got our 4 main stages, the DC input, or your power rail, and then the DC to DC conversion, where we step down that input voltage, and then our voltage regulator module, and then finally the IC itself. And between all these, we've got some decoupling and filtering going on. Here, kind of moving towards the IC, where we provide cleaned power, or moving back away along the return path. More like filtering. And all throughout, we're going to use decoupling and filtering capacitors to absorb and deliver charge as needed, whether it's lower frequency situation where we need a higher capacitance value, or a higher frequency situation where the capacitance values tend to need to be smaller. So first, we'll go through the decoupling and take a little closer look. So one of the most prevalent uses of capacitors in low voltage DC designs is to decouple the IC from the power supply circuitry. So basically the IC can use this set of capacitors and bypass the power supply if or when needed, which is where they get their other name from, bypass capacitor, since they can effectively act like a local reservoir of energy, where they help maintain like stable voltage levels and supply fast power to prevent any voltage droop, like if many of the devices demand power all at the same time, or they can protect the IC from any high frequency noise on the bus, and can also like decouple RC delays that can also lead to lowering the bus levels. So in these ways, kind of noted here, eliminating high frequency noise, decoupling RC delays, and preventing voltage droop, that bypass capacitors eliminate delays in supplying power, which is a critical issue with high performance embedded devices where we need to ensure regulated voltages and keep them within our increasingly tight tolerances. So our little IC, bypass capacitor, and just kind of following some conventional wisdom, we usually just mount them kind of as close to the IC as we can get them. So first, let's talk about impedance. So why is impedance important? Well, we need an impedance to be on the same level or lower than whatever the impedance of the target IC is, so that our power distribution network can be decoupled properly and efficiently. So first, we need to calculate our target impedance, which can Sorry about that, first time presenting on Zoom. So first, we can calculate this target impedance, which can be done by just applying another variation of Ohm's law. We take Z target, which is equal to the voltage rail, times whatever percent ripple over 100 divided by the maximum transient current. And we'll take it, transform it into the time domain, and then integrate it, and then subtract out the step response from the voltage regulator module. And I hope you guys like that block diagram, because I'm not about to give a math lesson there. Okay, so now let's just look at an example where we'll try to work our system down to the calculated impedance. So kind of back in the early days of PDN design, which I wasn't around for, it was kind of the thing to just put a number of 0.1 microfarad capacitors close to the active device leads. And this approach was sufficient as long as that active device didn't generate too much significant transient noise above the SRF of the bypass capacitors. But kind of just to demonstrate this, so we'll start with the target impedance of 100 milliohms, lower frequency target 10 kilohertz, and upper frequency maximum target of 500 megahertz. And so looking at this, we're just going to start off with a 1 microfarad ceramic capacitor, and we see that we have an SRF of 6.5 megahertz. But our impedance isn't quite what we wanted at upper and lower bands. You can see that we're a bit high on both ends. So we'll add another of this exact same capacitor in parallel. We're calling this cascading. There we have it. And we can see that the self-resonant frequency or series resonance frequency doesn't change at all when we add them in parallel. And the impedance does come down a little bit closer to our, closer at our target frequencies, but still we're too far off. So we've got 2 in parallel there. And now we're going to go from 2 all the way to 10 of these identical capacitors in parallel together. And we're still not really meeting our target at our upper and lower frequency bands. But we can see some benefits from this. Overall, we've lowered the impedance across our frequency range. Not enough, but we can see that it has come down a little bit. We've also reduced the total ESR. And we can also reduce the physical inductance by using multiple smaller capacitors versus having one larger capacitor, which tends to have higher ESL. And conveniently, putting caps in parallel doesn't affect the ESL. So using multiple small caps can help you reduce your ESL and therefore improve efficiency. So we can see that we do have some benefits already, but modern microprocessors and such like that we now demand that we now design our PDN a bit more systematically than just cascading more and more of the same capacitors in order to meet our impedance needs. So let's see what we can do. So taking another example, we're going to work this impedance down at our target frequencies, our upper and lower band here, to 100 or lower than 100 milliohms across this frequency band. So it looks like our lower frequency is around 10 megahertz, and our upper one is around, like, I guess, 400-ish megahertz. And first off, we're starting with a tantalum polymer capacitor with 330 microfarads, which is a pretty large cap value. So here, over on our lower frequency, at our lower frequency torque bound, we can see we're doing pretty okay. Our impedance is down below 100 milliohms, which is our target for the IC. But over here at the upper bound, not so much. So let's try to fix that. Wow, looks like there's a lot going on here. So let's just take this step by step and see what happens. So we added a 1 microfarad ceramic capacitor to the mix. Now this is quite a bit lower value than the 330 we started with. That's because the issue is over here in the higher frequency range. So higher frequencies usually demand lower capacitance values. So we can see that it did come down just a little bit, but we're still way out of bounds. But an interesting thing that came up now is this point here called the anti-resonant point. So the impedance here is actually higher than the SRF of either one of these capacitors that we've used. And you can see that it occurred right there where the two impedances of the capacitors crossed. So this is something that we need to keep up with and be on the lookout for as we move further along in our design, trying to bring the impedance down to an acceptable level. Okay, so we didn't have quite enough cap there to get the higher, to meet the impedance at the higher frequency bound. So we basically doubled it here, adding another one of the same ceramic capacitors in parallel. And so we can see here that we've brought the impedance a little bit closer to the target at our upper limit. And we see the overall ESR is going down and things are looking good, but we're still pretty far off from the target. So let's look at this. So it's still the higher frequency that we're targeting. So we added yet a smaller capacitance, a 10 nanofarad ceramic capacitor. And at our upper bound, you can see there that we've brought the impedance even closer to our 100 milliohm target. But with this additional different capacitance value that we've added into the mix, we've got yet another anti-resonant point cropping up here. And it's just slightly higher than what we want. But we're still working on our main target frequency over here. So we're still going to be trying to pull this down while also trying to keep these anti-resonant points down. So we increased that one count 10 nanofarad capacitor to 7, and we're even closer to the target now, but that anti-resonant point has become a problem. So let's move on and see what we can do. So we're going to put in, again in parallel, another smallish value capacitor. We've added a 47 nanofarad, and you can look and see that we've reined back in those anti-resonant points and also brought our impedance at the upper limit down closer to the 100 milliohm impedance target, but we're still not there. But we see that 47 nano is taking us in the right direction, so we're going to add some more of those. And now we're so close, everything's looking good. The impedance at all these anti-resonant points are down below the 100 milliohm target. We're still good over here on the lower end, and we're getting even closer at the upper bound. So let's continue and see if we can get it to come down just a little bit more. What can we add? Since we were already pretty close, we're just going to add like a 4.7 nanofarad capacitor in parallel. But look what happened. We're doing so good. But then these anti-resonant points are stepping back out of line. And now all these small caps have had an overall effect, and our lower frequency bound has come up a little bit as well. So not good. Ooh, but after we add our little 1 volt bias voltage here, and we're going to increase those 4.7 nanofarad capacitors to a 7 count versus the 1 that we had only added. And look what we've got now. We've pulled the entire thing down below 100 milliohms target impedance across our entire frequency range. And we have used a combined capacitance value of 331 microfarads, all at 10 volts here cascaded in parallel. So it looks like we're done. I'm sweating. Well, it wasn't that hard, it's just really hot. But so we've had some success here. So now that we can see kind of the process of getting this impedance all down to the target that we calculated, I would just like to show you real quick where you can do this on our website. But just before, let's get the big picture here, just to keep in mind what our overall goal is. So this was done, all to get the needed target impedance out of this processor over here, so that this processor can effectively and efficiently function. So real quick, so we started with our higher value capacitance 330 to take care of lower frequencies, and gradually added smaller capacitance values to take care of the higher frequencies, all while trying to maintain a grip on the anti-resonant points that pop up when you have the different values put together in parallel. So just take a look at the tool that I used to do this here. So this is one of Kemet's simulations tools. It can be found on our website, or you can go to ksim.kemet.com. And so first, over on the left-hand panel, you can select whatever capacitor you want to start with. You can add however many that you need. And then below the graphs, you can enter the quantity. So default, you'll just start with 1, but if you need to add more cap values like we did throughout that process to bring the impedance down even further, you can just go and type in whatever value you want, and KSIM will simulate that for you. And then up at the top, you just need to make sure to combine impedances so that you see the total combined impedance of all the capacitors that you've added to the simulation. So before we move on, we've got a real world example here. This figure shows a power distribution network, or PDN, proposed by somebody at Intel, Larry Mosley, in which the move from the power source to the microprocessor circuit comprises decoupling transitions from bulk to mid-level to low ESR, low ESL as the capacitance values get smaller and smaller because your frequency is getting higher and higher. And finally, all the way down to the internal die capacitors. And the PDN impedance seen by the load is the parameter that determines the peak voltage deviation during the fast transients. So the system requires this low impedance network over all of the frequencies to ensure that the deviation remains within an allowable voltage range or threshold. So one common factors for all this decoupling capacitors, the lower the ESR and the ESL, the better the decoupling strategy will be, the more efficient it will be, the better it will perform. Typically, as we can see over here, a combination of like ceramic and tantalum and even aluminum electrolytic polymers offer a good decoupling situation. And then smaller capacitors, as we move on with smaller values and low series inductance, provide the faster frequency decoupling. And as we just move, we kind of follow that trend all the way down to the 1 gigahertz. So that wrapped it up for the decoupling. Now we're going to kind of look at the flip side of the coin, where we're going to go over filtering. So what's kind of our aim with filtering? Well, a few things, but 2 basic ones that we see here. We want to block any unwanted signal, or we want to pass along a desired signal. So kind of a big overview example. Let's look at this nicely simplified DC to DC converter. So in this representation, CN is in parallel with the input voltage, and its main purpose is to act as a reservoir capacitor, our decoupling capacitor that we just went through. So it reduces the ripple voltage amplitude seen by the switcher. So the characteristics that are important here are ESR impedance, like we looked at. And then on the other side, we have C out, which is also integral to the switcher operation. It's our filtering cap, and it's basically charging and discharging on the switching frequency so that the voltage stays nice and constant with only a slight ripple. So a lot of care has to be taken when choosing this type of capacitor as well, so that the parasitics will have as little impact on the efficiency of the converter as possible. And of course, we also use inductors here to help on the C out, or on the filtering as well. Use it there in combination with your C out capacitor. So let's just take a little bit of a look at the capacitors themselves. It's like a capacitor is just a capacitor, right? Well, that's wrong. There's so many different types, and they all have their benefits and drawbacks. So just real quick, we'll look at some of the main ones for each of them. So when determining what you need. So while each circuit will be different, there's kind of a general rule of thumb for selecting input and output caps. So input ceramics normally or film for voltages greater than 40 volts, or if you have a low cost design to fit to, you can use aluminum electrolytics. And then polymers and tantalums are more suited for things kind of sub 400 volts. So quickly, let's see why. So ceramic capacitors are pretty good for quick frequency response or lower frequency. They're just good with frequency all around, and particularly good for lower voltages, since that's where they tend to be cheaper or more cost effective. Film is pretty okay, but if the frequency is higher, you might run into some dissipation factor concerns, so there's something to be on the lookout for. Also, less than 40 volts isn't very practical for film technology, just due to some of the nuances in the film materials that are available. Aluminum electrolytics are pretty great at lower frequencies, but tend to not be the best as frequency increases, since they suffer from what's called capacitance roll-off, where you actually lose some of your capacitance as the frequency goes up. They also have some higher ESRs than what you might want. But if your driving factor is cost, then they can be effective enough to function properly across most practical voltages. And then, moving on from aluminum electrolytic, you have the aluminum polymer. And these handle frequency a little bit better than lytics, and it's also good across different voltages and cost effective as well. They're also a smaller form factor and lower ESR. And then under aluminum polymer, we have next just our polymers, which when we say polymer, usually here we're referring to our tantalum polymer, which has a little bit of a limited voltage range available the higher up you go, but for anything sub 40 volts, it's pretty good. Also, you have lower ESRs than maybe the traditional MnO2, and better ripple current handling capability than its predecessor, the tantalum MnO2. But then you could also use the tantalum MnO2. So it might be it could be better at frequency response. It tends to have low performance there, and it's not great for higher voltages. This is mostly due to our derating policy that we put out. We highly recommend that you do 50% voltage derating for the tantalum MnO2s. So you might find a cap that's rated 40 volts, but effectively you'll only be able to use it at 20. So anything higher than 40, not so great for, but if you're in the lower range, the tantalum MnO2 can also be an option, just depending on the demands of your system. And then inductors are also involved in the filtering. And the inductors to be used, there with C out, basically we have two chemit options. We have our metal composite inductors, which have pretty nice soft saturations. They're good up to about 40 amps of current, but the core loss tends to be a little on the high side, or higher than the ferrites at least. So our ferrites here, these are mostly our TPI one-turn ferrites. They're good up to 70 amps. And they do have better efficiency with the core loss, since they have lower core loss, so that in turn leads to better efficiency, but they do have a harder saturation profile. So it's a kind of give and take. You just have to determine what's most needed for your specific system. So a quick example of an input filter here, just to show the benefit of using input filtering, which I think pretty much everybody will use. We can take it here on the left side without any input filtering, and we see that we have 2.78 volts ripple. Or we can take advantage of some chemic caps and inductors, do a little input filtering, and rein that all back into only 0.47 volts of ripple. So conclusion, by chemic capacitors and inductors. And then just let's look at just an overall view showing where we use both the decoupling caps and the filter caps. So it's kind of worth pointing out that in today's systems, we have multiple converters attached to the same main power supply. And this can create design concerns in terms of having enough power reservoir available at both the input and the output of each section. And as a result, we need to take care to place the capacitors near to the converter input and output so as to minimize their parasitic effects and the impact it has on the system so that it doesn't corrupt it too much. So we can see here all this coming off of the same power supply. We want to get the decoupling capacitors as close we can to the input rails there, and then also on the output. So ultimately, what matters is that the active device should be connected to an impedance low enough that the current transient generated will be within our noise voltage limits. So I guess when you consider that, we assume a matched transmission line with suitable characteristic impedance feeding that active device. And what really matters there is that the impedance that feeds it, that low one that we calculated, reaches the end device or the IC. So in which case, as long as you can do that, precise location might not be too important, but when in doubt, just place them on the input and the output. So just running through our conclusions here, just want to look at the highlights of what we covered. When decoupling and filtering are not the same. Optimized decoupling requires cascading mixed capacitor technologies and values in parallel, as we saw all throughout that example. Location of the cascading decoupling are best placed in respect to the load, to where the load becomes, the location where the cascading decoupling capacitors are placed in respect to the load becomes critical as the target impedance frequency increases, also as we saw throughout our examples. Application requirements can dictate the filtering component selection. As we saw, different capacitor technologies have different parasitics and drawbacks that you need to consider. Power distribution systems require both decoupling and filtering capacitors and inductors. And ESR is also one of the main important things when looking at the size of the capacitor bank. So, that concludes the presentation. All for your attention and joining. We might have a little bit of time. We have about 3 minutes, I guess, for Q&A, or if you have any comments or further questions or would like to know anything else, you can contact me at Olivia Williams.
Okay, thank you, Olivia. Yeah, we actually have a question. What tool are you using to find impedance in ESR? I think you showed a little bit of that, but I think you were asking about the CASM.
Yes, let's go back to that slide real quick. So this is one of our commit design simulation tools. If I can get back there. Hold up, this might be easier. Okay. Where are we? Okay, so this tool can be found on our website, commit.com. So you can, I think it's found through the engineering center or design, no, go to design tools and you can find it under there. We have several design tools actually, but this is what we use throughout all the examples. This is a direct link and I'm sure we'll be providing you all a PDF version of this where you could just copy and paste it into your web browser, or you can go through the Commit website. So it has quite a broad selection of all of our ceramic capacitors available, as well as our tantalum and tantalum polymer, and even a few aluminum polymers, I think. So it's a pretty handy tool. It is a work in progress. We are expanding what's available in this tool every day, getting more capacitance values. We're also beefing up the inductor portion where you can look at losses for your inductors as well. The focus of this was the capacitors, but the inductor tool is available there as well if you would like to look at that. So.
Okay. And we have just about a minute left, so maybe you can take one more question. Okay. So the question says the frequency targets would normally be given or found in the datasheet, for example, of microcontroller, or which is the criteria to be taken into account when using decoupling capacitors?
So the criteria, so I guess if there's a frequency target giving in the microprocessor that you're using, that would probably dictate the frequency bounds you're going to look at. So I guess you would target your impedance at those frequencies given, I think is what the question is getting at. If not, please reach out and we'll flesh it out better.
Okay. Well, this is all the time we have. Thank you once again, Olivia, for this presentation. Thank you to all of our audience for joining us today. Until next time, I wish you a pleasant day and goodbye. See you next time.
Thank you. Bye.
Thanks. Bye-bye.